Hello, welcome to lecture 4 of the course on quantum entanglement and non-local games. Today we look at a generalization of the CHSH game, which is called the XOR game, and we'll also look at the quantum or entangled strategies for XOR games. I'll just shortly define what these are. So an XOR game is a generalization of the CHSH game. So if you recall, in CHSH game, we had Alice and Bob who received inputs SNT, and these lied in the range 0 and 1. And they produced an outcome A and B each, which were constrained to lie in the 0-1 regime. We also had the ±1 case as well. And here the value function was defined as 1 if the XOR of outcomes equals the AND of inputs, and 0 otherwise. So here note that the valuation is a function of A XOR B, S and T. So what A and B are independently does not matter. What ultimately matters is their XOR. So this is a generalization of something we call as the XOR game. So in the ±1 regime, our outputs A and B are going to be in ±1, and over there we can also talk about V lying in ±1, and this is because in this case, if V lies in ±1, it's easy to define bias. So in an XOR game, what happens is that this outcome VABST. So here now I'm talking about the case where where A and B are both ±1. So here V of ABST can either be +1 and -1, and for it to be +1, or AB, the product has to be either +1 or -1, depending on whether our SNT, like depending on the values of SNT. So what I can write it is that it's equal to -1 to the power G of SNT for some function G, because G is the function which tells me that whether I want AB equals +1 or AB equals -1 in the winning condition. So in the XOR game, the formal definition is that the valuation can depend on S, T and XOR. Now we are saying that since A and B are ±1, the valuation can ideally depend on AB, and it can depend on S, and it can depend on T. Now the only form of the case where the output is either ±1 can be that either valuation is 1 if AB is -1, or it is 1 if AB is +1. Either of these two has to be true. If it is 1 in both cases, right, if it is 1 whether AB is +1 or -1, then actually those inputs are redundant, right? So we can throw away those input cases, because that means that we are anyways winning the game. So we can restrict ourselves to cases where we win in only one case, when either AB is +1 or AB is -1. Right, so AB being +1 corresponds to A XOR B being 0 in the 0-1 output case, and AB being -1 in the product case corresponds to A XOR being 1 in the 0-1 case. Okay. So now what I can do is that I can say that from the above definition, I can say that here the valuation is going to be AB times -1 to the power of some function of SNT, which is going to be G of S, T. So we can take this to be the definition of an XOR game, for plus minus 1 valued outputs and plus minus 1 valued value function. So here we can talk about a quantum strategy, and we can talk about just bias as well. So a quantum strategy would involve Alice and Bob sharing an entangled state. So let me call it ket psi AB. Here on input S, Alice measures a binary variable AS. Actually a binary observable, I should say. And on input T, Bob measures a binary observable V sub T. Now I can define the bias here, and they are measuring on their share of this entangled state, psi AB. The bias of this game will be sum over all inputs S and T, the probability of S and T, which is indicated by the parameters of the game, times minus 1 to the power G sub ST times the expected value of AB, which is psi AS tensor BT psi. Now in order to analyze this, what we'll do is that we'll separate this term into two parts. So what do we write? We write psi AS tensor BT psi as psi AS tensor I tensor BT psi. And now what I can do is that I can define this part as WT, and this part can be defined as Vs. So we are defining WT as I tensor BT psi, and Vs is defined as AS tensor I activate psi. So note that psi is a unit vector and the binary observable is always unitary. So WT and Vs are also unit vectors. So in this regime, I can express the bias of the game as sum over St pi St minus 1 to the power GST Vs dot WT. Yeah, it's V sub S WT. So therefore the optimal bias, if I define the optimal bias, will always be less than equal to the supremum over unit vectors Vs and WT sum over St pi St minus 1 to the power GST Vs to WT, right? Because any entangled strategy will provide me these values of Vs and WT, and this particular value which I'll get for this bias will be upper bounded by the supremum over all such Vs and WT, right? So even the best entangled strategy will be upper bounded by this value. Now what our claim is that these happen to be equal, and this is also known as the Serelson's theorem, that beta star G, the optimal bias, is exactly equal to supremum over Vs and WT, such that norm Vs equals to 1, norm WT equals to 1, sum over St pi St minus 1 to the power GST Vs to WT. And if you observe that this quantity is much easier to optimize, because here we are only optimizing over vectors, whereas earlier if we would have wanted to optimize over AS and BT and psi, then we would have to optimize over all possible observables. So we can actually restrict ourselves to optimizing over vectors itself. And it looks strange that why it should be true, but rather but it is so that it is indeed true. And now we'll see the proof of this theorem. So before proving this, we need to actually show a lemma. So, okay, so the proof will proceed as follows, that given Vs and Wt, and let us say that these are m-dimensional real vectors, will define operators As, Bt. So Vs for S in S and Wt is T in T. Will define these corresponding operators and an entangled state such that Vs dot Wt equals psi As tensor Bt psi. So if we are able to do this, then we are done, right? Because if we can define these possible As tensor Bt in such a way, then what we can do is that given Vs and Wt, I can always substitute it back here, and that will give me a strategy which corresponds to measuring psi in the observables As and Bt. So the thing is that we need to define operators specifically which are actually binary observables As and Bt, such that Vs and Wt, the inner product, equals psi As tensor Bt psi. If we are able to do this, we are done. So how to perform the same? So to show this, we will actually now use a lemma which says that for all natural numbers m, there exists a set of m observables on m-1 qubits. So what are these m observables? I am going to call them u1 up to un, such that ui uj equals to minus of uj ui for all ij, for all I not equal to j, right? So these are anti-commuting binary observables. This is what the statement of the lemma is. So actually I am taking m-1 observable, so I am taking m observables on m-1 qubits, but actually we can be more resource optimal here. We actually can do it within m-1 by 2 qubits, and in fact m-1 by 2 qubits is optimal, but here for the ease we will actually use m-1 qubit. So here we are not that much concerned about constant resources. So what I do is that I choose my binary observables, choose them in such a way that u1 will equal x tensor I so x on the first qubit, I on the second, I on the third, and then I on m-1. In case of u2, what I'll do is that I'll have a z on the first, an x on the second, and then identity on remaining. For u3, I'll have again z on the first, z on the second, x on third, and finally I on m minus 1. So here up to ui, which will be of the form z1 tensored, z2 tensored, zi minus 1 tensored, xi, and then rest all are identity. This is for I less than equal to m minus 1, and for I equals m, how do I define um? Will be z on all of these. So it will be z1 tensor z2 up to zm. Now take a couple of minutes and verify that each of these ui's is a binary observable, that is ui square equals to I for all I, ui tagger equals to ui for all I, and thirdly ui uj equals to minus uj ui for all I not equal to j. The first two conditions ensure that these are binary observables, and the third condition says that it satisfies the required conditions of our lemma, that is they indeed anti-commute. Okay, so now given this lemma, what we will do is that we will use these ui's to define our corresponding operators. So how to do that? So in order to design a quantum strategy, what we need to do is that we need to, so given Vs and Wt in Rm, so I need to produce psi As and Bt which satisfy the condition that psi with sandwich is As tensor Bt, the value is Vs dot Wt. So what I do is that I define psi as the maximal entangled state on these m minus 1 qubits. I define As to be sum over I Vsi ui, and I also define Vt to be sum over I Wti ui. So now we need to check that As is indeed a binary variable, Bt's are all binary observables, and thirdly psi with sandwiches As tensor Bt, psi equals to Vs to Wt. So I leave this again as a homework exercise, and I can give you a hint that when you will square this As, you will get ui square sort of terms, and you will get the terms which are of the form of ui uj and uj ui. So what you will need to do is that you will need to cancel the terms which basically consist of ui uj plus uj ui, because we have ensured that ui's and uj's are indeed anti-commuting. So this way you will be able to prove As square equals I and Bt square equals I. Proving that they are Hermitian is quite easy. For proving the third part, which is the main thing we need to do, you will need to use the three lemmas which we did in the first lecture, right? So if you remember, we had done those three lemmas, wherein we had talked about quantities such as As tensor I psi equals I tensor As transpose psi, and then we talked about psi which sandwiches As tensor Bt. The value turns out to be something like 1 over d trace of As transpose Bt. So those things you will need to use, but once you use them, you will be able to prove the third result easily. Yeah, so it's a good exercise. Yeah, so it will see if you have understood those lemmas also. So I leave it as a homework exercise, and once we have shown that this indeed equals psi times As tensor Bt psi equals Vs to Wt, what we have done is that so given any given any such vectors which optimize this quantity, what I can do is that for the ones which are indeed optimizing Vs and Wt, I can just substitute over here psi As tensor Bt psi. I can find the corresponding As Bt and the psi, which happens to be the maximally entangled state, and that indeed just gives me a strategy which achieves this supremum also. So if I know Vs and Wt which achieve the supremum, I can find the corresponding operators also, right? So this is a very nice sort of constructive argument we have had. And this is also known as Serelson's theorem. Okay, so yeah, and so basically what we say is that it's easy to design strategies for XOR games. We just need to solve a quadratic optimization problem on Vs and Wts. Yeah. Okay. Thanks. That's it for today's lecture. Hope you are all enjoying the course as well. Do like and subscribe if you haven't done already. That will help you keep updated with the new videos.